picture our planet from far above, a soft blue marble turning slowly in the black silence of space. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From this distance, you can see the whole world breathing. White clouds drift over the oceans like slow smoke. The continents look small and quiet, like islands in a great unbroken sea. That sea covers most of the planet. More than 2/3 of Earth is water, and almost all of that water is salty, deep, and dark. The oceans are not still. They are not even one single body of water in the way we sometimes imagine. They are moving. They are always moving. And much of that movement happens far below the bright surface, where no sunlight ever reaches. Beneath the waves, in the cold and the dark, there is a current. It is not like a river you can stand beside on a summer day. It is something much larger and much slower and much stranger. Scientists call it the global ocean conveyor belt. Some call it the thermohaline circulation, which is just a long word that means the flow is driven by heat and by salt. Whatever name you choose, it is the slowest, longest, quietest river on Earth. This hidden river touches every ocean. It begins in the cold seas near the poles, where surface water grows heavy and sinks into the deep. From there, it spreads out, drifting along the bottom of the world. It crawls south through the Atlantic. It bends around the tip of Africa. It loops beneath the icy ring of currents that circles Antarctica. It pushes north into the Indian Ocean and the Pacific. Then, after a journey of thousands of years, it slowly rises back to the surface, warms in the sun, and begins the whole long walk again. A single drop of water might take 1,000 years to complete this loop. Maybe more. The exact number is still debated. The conveyor belt is so slow, so deep, and so vast that we are still learning the shape of it. We can measure pieces of it. We can model parts of it on powerful computers. But the whole thing in motion, all at once, remains something we are only beginning to understand. What we do believe, with reasonable confidence, is that this slow river shapes the weather on every continent. It carries warmth from the equator toward the poles. It pulls cold water down from the north and the south. It feeds the winds. It nudges the rains. It helps decide which coastlines stay mild in winter and which ones freeze. It quietly hands out heat and moisture to one part of the world and withholds it from another. Whole climates, whole forests, whole deserts may owe their character to this hidden flow. And yet, when you stand on a beach and watch the waves come in, you cannot see it. The conveyor belt is invisible from the surface. It hides under thousands of feet of dark water. It moves at a speed slower than a sleepy walk. You could swim through part of it and never know, only by sending instrumentation instruments, by tracking the chemistry of the deep, by listening to the faint signals of cold water sliding along the sea floor, can we sense that it is there at all. This is the mystery we will sit with tonight. Not a finished story, but an open one. How exactly does this great loop work? How stable is it? Has it slowed before in the long history of the planet? Could it slow again? What would happen if it did? And could similar slow currents move beneath the icy shells of other worlds? In the dark oceans of distant moons, we have only just begun to imagine. For the next few hours, we will follow the conveyor belt around the world. We will go down into the cold plunge near Greenland. We will drift along the deep Atlantic floor. We will cross the bottom of Africa, ring the southern ice, slide into the Indian Ocean, climb back into the Pacific, and rise once more into the light. We will pause along the way to wonder about the things we still do not know. There is no need to hold on to any of it. Let the images come and go. Let the slow river carry you. Somewhere beneath the dark waves, water that fell as rain 1,000 years ago is still moving, still turning, still shaping the sky above you. And tonight, we are simply going to listen for it. To picture the great ocean conveyor belt, it helps to start with the simplest image. Imagine a long, slow river hidden inside the sea. This river does not have banks of stone or sand. Its banks are made of other water, water that is warmer or saltier or lighter. The river flows because of small differences in weight from one patch of sea to the next. And those small differences, added up across the whole planet, move more water than every river on land combined. Scientists often call this flow the global thermohaline circulation. That long word breaks into two simple parts. Therma means heat. Haline means salt. So the name just tells you what drives the river. Heat and salt. When water is cold, it grows heavier. When water is salty, it grows heavier too. Cold and salty water sinks. Warm and fresh water rises. From that one simple rule, the whole conveyor belt is born. The sinking begins in just a few quiet places on Earth. The main ones lie far in the north, near Greenland and Iceland, and far in the south, near Antarctica. There, the surface water gets very cold. Sea ice forms on top, and as that ice grows, it pushes salt out into the water below. So, the water near the ice becomes both colder and saltier at the same time. It grows heavy, and then, slowly, it begins to sink. The sinking is not a dramatic plunge. It is gentle, almost shy. The water slips downward at a pace slower than a person walks, but it does this across huge stretches of sea, day after day, century after century. By the time it reaches the deep ocean floor, it has joined a slow, broad flow that spreads out across the bottom of the world. The numbers behind this flow are hard to picture at first, so it helps to anchor them in familiar things. The conveyor belt moves about 100 times the water of the Amazon River. The Amazon is already the largest river on land, a giant green snake of fresh water cutting through the rainforest. Now imagine 100 Amazons, all flowing together, hidden in the dark below the waves. That is the scale we are dealing with. The belt also touches every ocean on the planet. It threads through the Atlantic, around the tip of Africa, into the Indian Ocean, and on into the Pacific. A single drop of water caught in the sinking near Greenland may not see the sunlight again for a very long time. The best estimates suggest a full loop takes somewhere near 1,000 years. Some parcels of water may finish faster. Some may take longer. The exact timing is still an open question, and different studies give different answers. Think for a moment about what that means. Water sinking off Greenland tonight while you lie in bed may not rise back to the surface until long after our grandchildren's grandchildren are gone. The belt is older than any city, older than any written language. It has been turning in some form for many millions of years, yet the version that turns today may not be exactly the version that turned during the last ice age. That, too, is part of the mystery. The belt is not one neat tube. It is more like a tangle of broad rivers and slow sheets of water, layered at different depths. Near the top, warm currents move heat from the equator toward the poles. Far below, cold currents move in the opposite direction, sliding along the sea floor. In between, water rises and falls in soft, patient swirls. The whole system breathes, in a sense, on a time scale we can barely feel. The water itself is mostly the same simple stuff you know. Salt water, a few dissolved gases, some minerals carried in from rivers and dust. What makes the belt special is not what it is made of, but how it moves. The smallest change in temperature, the smallest shift in saltiness, can tip a parcel of water from rising to sinking, or from sinking to rising. The belt is sensitive. It listens to the world around it. For now, hold this picture in your mind. A vast loop of slow water, hidden in the dark, stretching from pole to pole and from surface to floor. It carries heat. It carries salt. It carries memory in a way of climates from long ago. It begins where the sea grows cold enough to fall, and it ends, if it ends at all, only after a journey of centuries. Tomorrow's sections will follow that journey, step by quiet step, from the first plunge in the north. To understand how this great ocean conveyor came to be, we have to think about salt. Not the salt on a kitchen table, but the salt dissolved in every drop of seawater. It is the quiet ingredient that makes the whole engine turn. Without it, the deep currents would slow, stall, and perhaps stop altogether. Salt has been gathering in the oceans for billions of years. Rain falls on the land, soaks into the rocks, and slowly dissolves tiny bits of mineral. Rivers carry those minerals down to the sea. The water at the surface of the ocean evaporates back into the sky, but the salt stays behind. Over vast stretches of time, the seas grew salty in a slow, patient way. No one knows the exact moment the conveyor first began to flow in the form we see today. ocean basins themselves have shifted over hundreds of millions of years. Continents drifted apart. New seaways opened. Old ones closed. Each change altered the path that water could take. The belt as we know it is, in a sense, a young feature riding on top of a very old world. One leading idea is that the modern conveyor took shape after a narrow seaway between North and South America closed off. Roughly 3 million years ago, when the Isthmus of Panama rose from the sea floor, water could no longer slip easily between the Atlantic and the Pacific. The Atlantic, cut off from that exchange, became saltier. And saltier water, as it cools, grows heavy enough to sink. Some researchers think this small change in geography helped switch the deep circulation into the pattern we see today. Others argue the timing is not so clear, and that the belt may have shifted gently back and forth long before the isthmus closed. The question remains open. What is clearer is the simple physics that drives the whole thing. Cold water is heavier than warm water. Salty water is heavier than fresh water. When water at the surface becomes both cold and salty at the same time, it grows dense enough to sink. This sinking pulls more water in behind it, and a slow flow begins. The conveyor is, at its heart, a dance between temperature and salt. In the far north of the Atlantic, the conditions tip just right. Warm water arrives from the tropics. It gives up its heat to the cold polar air. As sea ice forms, it leaves its salt behind in the water below, because ice is mostly fresh. The water there grows colder, saltier, and heavier with each passing winter. Down it goes into the dark. This delicate recipe is part of why the conveyor is so interesting and perhaps so fragile. If too much fresh water arrives at the surface from melting ice or heavy rain, the salt grows thinner. The water becomes less dense. It does not want to sink as eagerly. The engine could lose some of its push. How much fresh water it would take to truly slow the belt, and how quickly are questions scientists are still working through. The age of any single drop of deep water is also part of the origin story. Water sinking in the North Atlantic today may not return to the surface for nearly 1,000 years. So the conveyor is not just a current. It is a clock water moving past the bottom of Africa right now first sank into the deep long before any of us were born, and may not see sunlight again until many lifetimes from now. There is something gentle in that thought. Each parcel of water carries a memory of the cold winter night when it first slipped below the waves. It carries dissolved gases, faint traces of the air it last touched, tiny grains of dust from the sky above the polar sea. As it drifts in the dark, it remembers. The salt that drives the engine has been growing slowly for so long that it almost feels still. But it is not still. It is shifting moment by moment with every river, every rain, every freezing of polar ice. The belt was not born in a single event. It was born in a long, patient assembly of small things. The rise of an isthmus, the cooling of the poles, the steady patience of evaporation. Some scientists wonder whether the conveyor has truly stable settings, or whether it has always been quietly rearranging itself. There may have been times in deep history when it ran faster, or slower, or in a different shape entirely. We sit tonight inside one version of a story that has many chapters we have not yet read. Far in the north, in the cold gray waters between Greenland and Norway, something quiet and enormous happens every winter. The surface of the sea grows colder and colder as the polar air drags warmth out of it. Tiny bits of salt, left behind when sea ice forms, slip into the water below. The water grows heavy, heavier than the water beneath it. And then, with no sound and no warning, it begins to fall. This falling water is one of the great engines of our planet. It is the northern plunge. It is where the conveyor belt takes its deepest breath. And to understand what is happening here, it helps to look at what this water is actually made of, because the story reaches much farther back than the sea itself. The water is mostly hydrogen and oxygen, of course. Two simple atoms bonded into the most familiar shape in the world. But those atoms have long histories. The hydrogen in the Greenland Sea is older than the Earth. It was born in the first few minutes after the universe began, when everything was hot and bright and dense. Every drop of seawater carries that ancient hydrogen still. Almost 14 billion years later, sliding silently into the dark. oxygen has a different past. Oxygen does not form in the early universe. It is forged deep inside stars, in the slow nuclear furnaces that burn for millions of years before a star collapses or sheds its outer layers. Each oxygen atom in the ocean was once locked inside a star that no longer exists. When that star died, it scattered its atoms into space, where they drifted through cold clouds and eventually settled into the young Earth. So every wave in the Greenland Sea is partly the ash of dead stars. How the water reached the planet at all is still an open question. One idea is that it came mostly from comets, dirty snowballs from the outer solar system that struck the young Earth and left their ice behind. Another idea is that the water was here from the very start, locked inside the dust grains that built the planet, and slowly worked its way to the surface through volcanoes. Both theories have evidence. Neither is fully settled. The water sinking off Greenland tonight may have arrived in many different ways, and we still do not know which path delivered most of it. Then there is the salt. The salt is what makes the plunge possible at all. Without salt, the cold water would not be heavy enough to fall. The salt in the ocean is mostly sodium and chlorine, two elements that were also cooked inside stars and scattered when those stars died. Over billions of years, rain has slowly washed these elements out of the rocks of the continents and carried them down to the sea. Every river is, in a small way, salting the ocean. The northern plunge depends on this slow geological gift. Dissolved into the water are also tiny amounts of other things: calcium, magnesium, potassium, traces of iron. The iron is especially strange to think about. Iron is forged in the cores of massive stars in their final moments, just before they explode. The same element that makes up most of the Earth's core, that gives our planet its magnetic field, is sprinkled in trace amounts through the seawater sliding into the deep. A single drop holds atoms from many different dead suns. The water also carries gases. Oxygen from the atmosphere, dissolved at the surface where waves meet air. Carbon dioxide, breathed out by every living thing and absorbed by the cold sea. Nitrogen, argon, tiny whispers of helium. As the heavy water plunges down past 2,000 meters, it carries these gases with it, locking them away from the sky for centuries. Some researchers think this slow burial of carbon is one of the most important things the conveyor belt does for the climate. How much carbon it stores and for how long is still being measured. The numbers are not yet firm. So the plunge in the Greenland Sea is not just a movement of water. It is a movement of ancient hydrogen, of star-forged oxygen and salt, of trace metals from exploded suns, of gases breathed by forests and volcanoes. All of it falls together into the dark, beginning a slow walk that will take 1,000 years, and we still do not fully understand what controls the rate of that fall. We know it slows in some decades and quickens in others. Why exactly remains an open question, drifting somewhere in the cold black water below the ice. Once the cold, salty water sinks in the far north, its long, quiet walk begins. It does not race. It does not rush. It moves at a pace so slow that, if you could ride along, you would feel almost no motion at all. A drop of water that plunges near Greenland may take 100 years just to creep down the spine of the Atlantic. The forces that move it are gentle, but they never stop, and they shape the deep ocean as patiently as wind shapes stone. The first force is gravity. Cold, salty water is heavier than warm, fresh water. When it sinks in the north, gravity pulls it down toward the sea floor, where it settles into a vast layer of dense, dark fluid. That layer must go somewhere. As more cold water keeps sinking behind it, the older water is nudged forward, the way a long line of people slowly shuffles ahead when new arrivals press in at the back. There is no engine. There is no pump. There is only weight pressing on weight, pressing on weight, mile after mile through the dark. Pressure becomes part of the story too. A mile below the surface, the weight of all that water above squeezes everything with enormous force. Yet water does not compress much, so instead of being crushed, the deep flow simply behaves like a slow, heavy syrup. It hugs the contours of the sea floor. It pours through underwater valleys. It pools behind underwater ridges, waiting, sometimes for centuries, until enough has gathered to spill over and continue south. The shape of the bottom of the ocean guides this hidden river the way the shape of a hillside guides a stream. Temperature plays its quiet part as well. The water that sinks in the north is near freezing, only a few degrees above the point at which it would turn to ice. As it drifts south through the Atlantic deep, it stays cold. The water above it is warmer, lighter, and lazier, and the two layers do not mix easily. They slide past each other like sheets of glass. Some researchers think small amounts of mixing happen along the edges, stirred by underwater waves and rough sea-floor terrain. But the exact amount of mixing remains an open question. The deep flow may be more isolated than we once believed, or it may exchange more heat with the upper ocean than current models suggest. The spinning of the Earth shapes the path as well. Because our planet turns, anything that moves across its surface, including a slow current of deep water, gets nudged sideways. In the northern half of the world, that nudge bends the flow to the right. In the south, it bends to the left. This invisible push, named after a 19th century French scientist, is part of why the deep Atlantic current hugs the western side of the basin as it travels south. It does not flow straight down the middle. It leans against the underwater slopes off the coasts of the Americas, drifting along their flanks like a quiet shadow. Tides matter too, in ways that are still being studied. The pull of the moon, and to a smaller degree the sun, raises the surface of the ocean twice each day. That same pull also stirs the deep water, especially where it brushes against ridges and seamounts. Some scientists think tidal mixing is one of the main ways the deep flow eventually rises back toward the surface, far away in other oceans. Others think wind plays the larger role. The balance between these forces is one of the unresolved puzzles in modern ocean science. There are no magnetic fields steering this current. There is no radiation pushing it along. The forces are old, simple, and patient. Weight, pressure, the slow turn of the planet, the breath of the tides. Together, they sculpt a hidden river that carries more water than every visible river on Earth combined. All of it moving at the pace of a tired walk. What remains uncertain is how stable this slow drift truly is. The deep Atlantic flow has worked this way for thousands of years, perhaps far longer. Yet, the forces that drive it depend on small differences in temperature and saltiness, and small differences can change. Some researchers wonder whether the current has shifted speed many times in the past, slowing and quickening in ways we are only beginning to read from old layers of mud and shell. The forces at work are gentle, but they are not guaranteed. They are a balance held in place by conditions that may not last forever. And so the dark water keeps drifting south, mile by quiet mile, carrying its secrets through the deep. We left the deep, cold water sliding south along the floor of the Atlantic, moving at a pace so slow it almost seems like stillness. Now picture it reaching the bottom tip of Africa, where the continent narrows to a single rocky point, and the sea opens into a wider, wilder place. This is where the belt must turn. And to feel what that turn really means, it helps to slow down and think about how big this stretch of water actually is. The southern tip of Africa sits in some of the roughest ocean on the planet. Here, the cold Atlantic flow meets warm water sliding down from the Indian Ocean, and the two great basins press against each other in a slow, swirling handshake. Scientists call this meeting Place the Agulhas region, after the warm current that hugs the African coast. It is one of the busiest crossroads in the sea, though no ship ever sees the deeper traffic far below. To get a sense of the scale, imagine shrinking the whole Atlantic Ocean down to the size of a swimming pool. At that scale, a blue whale would be smaller than a grain of rice. A nuclear submarine would be a fleck of dust. The deep, cold layer of the conveyor, the part we have been following, would be a thin sheet near the bottom of the pool, drifting from one end to the other in a motion so slow you would never see it move with your eyes. Now, bring the ocean back to its true size. The water moving around the bottom of Africa carries, every single second, a flow that is many times larger than every river on earth combined. Take the Amazon, the Nile, the Mississippi, the Yangtze, the Congo, all of them pouring at once. The deep current here moves more water than that, quietly, in the dark. With no sound a human ear could ever pick up. Yet, that same current creeps along at about the speed of a slow walking snail. A drop of water that rounds the cape today might not reach the next great basin for years. The volume is huge. The pace is gentle. That is the strange double truth of the conveyor. It is both enormous and patient, like a glacier made of liquid. If you could place a single drop of dye in the deep water near Greenland and follow it south, it might take that drop several decades just to reach the latitude of Cape Town. And the Cape itself is only a waypoint, not a destination. From here, the flow swings east into the wide southern sea that wraps the whole planet without ever touching land. So the journey, in a sense, is only beginning. Think about that in human terms. A child born on the day a drop of water leaves the Greenland Sea might be in middle age by the time that same drop slips past the southern tip of Africa. By the time it finishes its full loop and rises again to the surface, that child could be long gone and their grandchildren grown. The conveyor moves on a timescale that outlasts us. There is still real mystery here, even at this familiar bend in the route. Researchers are not entirely sure how much warm Indian Ocean water leaks westward into the Atlantic at this meeting point. Some studies suggest the leak has grown in recent decades. Others wonder whether it has stayed steady for centuries. The honest answer is that we do not yet know, and the question matters because that warm leak may help feed the very engine that drives the belt to the north. It helps to picture the geography in simple shapes. Africa, a great wedge pointing south. To its west, the long Atlantic basin. To its east, the open Indian Ocean. Below the wedge, a narrow gateway where two oceans almost touch. Through that gateway, ribbons of water braid past each other, some warm, some cold, some shallow, some deep, all moving at different speeds and in different directions at once. It is layered, like the pages of a book turning at different rates. Standing on a cliff at the Cape, a person sees only blue water and white surf. They cannot see the slow rivers below, the cold, deep flow heading east, the warm, shallow flow heading west, the eddies the size of small countries that pinch off and drift away into the Atlantic. all of that hidden traffic moves on, night after night, year after year, while the surface keeps its quiet, ordinary face. And the conveyor keeps turning. Around the bottom of a continent, it has been rounding for longer than any human story. Imagine for a moment that you could lift away from the warm shoulder of Africa and drift south, following the cold water as it slips into the great empty sea below the continents. The water moves quietly here. Above the surface, the sky grows pale, then silver, then the color of old steel. The waves grow longer, taller, slower. Below you, the deep current you have been following all this time begins to mix with something even larger. A ring of cold water that circles the entire bottom of the world. This is the Southern Ocean. It is the only ocean on Earth without an end. It flows around Antarctica in one unbroken loop, with no continent in its way, no shore to turn it aside. If you floated above it and looked straight down, you would see a band of dark blue water wrapping the planet like a wide gray ribbon. The clouds above it sit low and heavy. The light feels thin, as if the sun has grown shy. Down on the surface, the wind never quite stops. Sailors gave the latitudes here strange, lonely names long ago. The roaring 40s, the furious 50s, the screaming 60s. The water responds with waves that can rise as tall as small buildings, gray and silver, and streaked with white foam. Yet somehow, watching from above, the whole scene still feels slow. The swells move in long, deep rhythms, like the breathing of something enormous and asleep. Closer to Antarctica, the color of the sea begins to change. The blue grows darker, almost ink-like, and patches of pale jade appear where ice has melted recently. Then come the floes. Thin plates of sea ice at first, scattered like broken glass. Then larger sheets, lying flat and white against the dark water. In the deep cold of winter, these sheets join into a single shell that doubles the size of the frozen continent itself. In summer, much of it melts back into the sea, releasing fresh water in long, slow pulses. And around all of this turns the great current. Scientists call it the Antarctic Circumpolar Current. It is the strongest current on Earth, moving more water than every river on every continent combined. It does not rush, it glides. If you could stand on its surface, you might not even notice it. But hidden inside that gentle drift is a flow so wide and deep that it carries the memory of every ocean on the planet. The Atlantic water you followed south arrives here and joins it. The Pacific and the Indian feed into it as well. The cold ring stirs them all together, like a slow spoon turning in a vast, dark bowl. Some researchers think this circling current is the true heart of the global conveyor. Without it, they suggest, the deep waters could not mix the way they do, and the conveyor belt might not exist at all. Others wonder if the mixing is shared more evenly with other parts of the ocean, with the Southern Ocean acting more like a hub than a heart. The question is open. The instruments are still listening. From above, the textures keep shifting. There are bands where the sea looks almost polished, smooth as wet stone. There are bands where the wind tears the tops off the waves and spreads them into a white haze. There are places where the cold water rises from the deep, bringing up tiny living things that turn the surface a faint, milky green. Whales pass through these green patches in slow, dark shapes. Seabirds skim the troughs of the swells without ever seeming to flap their wings. And then, in the far south, the ice cliffs of Antarctica appear. They rise straight from the sea in long white walls, sometimes hundreds of feet tall, glowing pale blue where the light catches the older, denser ice. Pieces break off and drift north as icebergs, some flat and broad like floating tables, others sharp and strange. They will travel for years before the warmer water finally dissolves them. What you would be looking at, if you could truly float there, is one of the quietest engines on the planet. A cold ring turning slowly, with no beginning and no end. It cools the water that arrived from the north. It hands water off to the Indian and the Pacific. It holds the whole conveyor together with a steady, patient turning. How exactly it does this, in every detail, is still being worked out. Models disagree. Measurements are sparse. The Southern Ocean keeps much of itself hidden under storm and ice. For now, it simply turns the way it has turned for a very long time. the waters leave the cold ring around Antarctica and begin a slow, sideways drift into the Indian Ocean. This is one of the least watched parts of the Great Loop. The Indian Ocean is the smallest of the three big oceans the belt passes through. It sits between Africa, Asia, and Australia, with no open path to the north. That closed top edge gives it a strange and lonely shape. Picture the deep water moving in dark blue layers, far below the bright surface. Above, the sun warms the shallow sea. Below, the cold flow from the south slides in like a slow, heavy breath. The two layers do not mix easily. They glide past each other, separated by faint walls of temperature and salt. The belt does not punch straight through the Indian Ocean. It curves and folds and lingers. Some of the cold, deep water creeps up the eastern side near Australia. Some hugs the western side near Africa. The flow is broken into many quiet branches, and the branches change with the seasons. The Indian Ocean is the only ocean whose surface winds reverse twice a year, pushed by the monsoons. Those shifting winds press down on the upper sea and tug at the layers below. What makes this detour so strange is how slowly the deep water rises. In the Atlantic, the cold flow stays mostly low, hugging the sea floor. In the Indian Ocean, parts of it begin a long, gentle climb. Warm water at the top must eventually be replaced. Cold water from below must eventually return to the sun. Somewhere in this quiet basin, that trade begins. But the exact paths remain unclear. Researchers have mapped the broad shape of the flow using floats that drift at fixed depths. These small machines sink to chosen layers and ride the currents in silence for months. When they surface, they send back a few numbers about where they have been. From those numbers, a faint sketch of the deep Indian Ocean appears. It is only a sketch. Vast stretches have never been measured at all. One open question is how much of the belt actually passes through the Indian Ocean and how much skips it. Some models suggest a large share of the cold southern water enters here and slowly warms on its way to the Pacific. Other models suggest only a thin branch passes through, while the main flow stays farther south. The truth likely sits somewhere in between, and it it may shift from decade to decade. There is also the puzzle of the Agulhas leakage. At the southern tip of Africa, warm, salty water from the Indian Ocean spills around the corner into the Atlantic in great spinning eddies. These eddies are like slow whirlpools the size of small countries. They carry heat and salt the wrong way, against the usual direction of the belt. Some researchers wonder if this leakage helps keep the whole loop steady. Others wonder if it could grow stronger and tip the balance in some unknown way. The question is open. Deep below all of this, the sea floor of the Indian Ocean is wrinkled with ridges and trenches. The cold flow must wind around these underwater mountains. In some places, it speeds up as it squeezes through narrow gaps. In others, it slows and pools in dark basins for many years. The shape of the floor sets the shape of the flow, but the floor itself is still being mapped. Large patches of it are known only from rough satellite guesses. The water at these depths is strange to imagine. It is near freezing, even though the surface above might be warm enough for coral. It carries memories of the Antarctic from the day it sank long ago. It holds tiny amounts of oxygen, salt, and dissolved gases that act like fingerprints. By reading those fingerprints, researchers can guess how old the water is and where it has been. Some samples from the deep Indian Ocean appear to be hundreds of years old. They have been traveling unseen since long before any of us were born. That thought is worth resting on for a moment. Somewhere beneath the surface tonight, water is moving that last touched the sky in another century. It has crossed thousands of miles in the dark. It will cross thousands more before it ever sees light again. The Indian Ocean's quiet detour is one chapter of that long, slow story. The next chapter waits in the Pacific, where the loop turns once more and begins the longest stretch of all. For now, the deep water keeps moving, patient and unseen. In layers we have barely begun to map. From the cold ring that wraps the bottom of the world, our slow river of water turns north again. It enters the largest ocean on Earth, the Pacific, and begins one of the longest, quietest passages in the entire loop. This part of the journey is not glamorous. It is deep, dark, and slow, taking centuries to complete. And yet, it is one of the most important parts of the cycle, because here the deep water finally begins its long climb back toward the light. The Pacific is wide beyond easy imagination. It covers more of the planet than all the land combined. Beneath its bright blue skin lies a hidden basin of cold, salty water that has been traveling for hundreds of years already. By the time this water enters the Pacific from the south, it has not touched the surface in a very long time. It has not felt sunlight. It has not been stirred by wind. It has only drifted, patient and dark, through the abyss. Scientists believe this leg of the trip is where the conveyor slows to its most gentle pace. Some estimates suggest the deep Pacific water creeps along at speeds slower than a sleeping snail. A single drop might take 1,000 years to cross from the Antarctic edge up toward the equator. The water itself becomes a kind of clock. By measuring the chemicals inside it, researchers can guess how long it has been hidden away from the sky. The rhythm of this passage is unlike anything we know on land. On the surface, the world pulses with quick cycles, day and night, summer and winter, tides that rise and fall twice a day. Down here, none of that matters. The deep Pacific knows only the slow heartbeat of the planet itself, the patient breathing of the whole ocean system over centuries. It is a rhythm so long that no single human life could ever feel it directly. And yet, the water is not still. It must rise. Somewhere along this journey, the deep current begins to mix upward, lifted by gentle forces that scientists are still trying to fully understand. One idea is that underwater mountains and ridges stir the water as currents flow over them, slowly pushing it toward the surface. Another possibility is that tides themselves, pulled by the moon, reach deep into the ocean and help lift the cold water back up. Some researchers wonder if both forces work together, while others suspect there are stirring processes we have not yet measured. The question of exactly how the deep water climbs remains an open one. What we do know is that the climb is slow and spread across enormous distances. The water does not rush upward in a single place. It rises gradually across vast stretches of the Pacific and Indian Oceans, like mist lifting from a quiet valley at dawn. As it rises, it slowly warms. It softens. It begins to remember the sun it has not seen in 1,000 years. This long climb is the great inhale of the conveyor. The northern plunge in the Atlantic was the exhale. Together they form a breath that takes 10 centuries to complete. Some scientists describe the whole system as the slow lungs of the planet, drawing in cold water at one pole and releasing warm water at the other. Whether that image truly captures the physics is debated, but it gives us a feeling for the scale of time involved. There are still many open questions about this Pacific leg. We do not know precisely how much water rises in each region. We do not know if the climb has stayed steady through Earth's long history, or if it has sped up and slowed down with the ice ages. Sediment cores from the Pacific floor hint at changes, but the records are incomplete and hard to read. One theory suggests the deep Pacific acted as a kind of storage tank during past cold periods, holding water away from the surface for even longer than today. Another theory pushes back, arguing the patterns were different than that. The debate is not yet settled. For tonight, let the picture be enough. Picture water that has not seen the sun since the days of ancient civilizations. Picture it rising, drop by drop, across an ocean so vast it could swallow every continent. Picture the slow, patient rhythm of a planet breathing through its deepest layers. Somewhere beneath the Pacific, right now, a current that began its journey before your great-great-grandparents were born is finally, quietly, beginning its climb back toward the light. And no one yet knows exactly how. Picture a single drop of water beginning its slow walk in the cold air above Greenland. It grows heavy with salt. It sinks, and from that moment forward, it may not see the sky again for 1,000 years. That is the rough estimate scientists give for one full loop of the great ocean conveyor. 1,000 years, maybe more, maybe less. The exact number is still an open question, and it changes depending on which path the water takes through the dark. To grasp this, it helps to think about what 1,000 years really means down there. While that single drop drifts through the deep, whole civilizations rise and fall on the surface above it. Forests grow, burn, and grow again. Coastlines shift. The drop knows none of this. It moves at the pace of a slow walk, sometimes only a few centimeters each second, pulled along by water sinking somewhere far away. The ocean does not hurry. This is why the conveyor is sometimes called a memory. The water moving past the coast of Africa today may have last touched the air when medieval villages still stood in Europe. The water rising in the Pacific may carry the chemical signature of storms that ended before written history began. Every loop the belt makes is a long, quiet record of a vanished sky. The neighbors of this hidden river are many. Above it sits the surface ocean, warm and bright and full of life, stirred by winds and sunlight. Below it lies the sea floor, dark and cold, and dotted with strange hills and trenches. Beside it run other currents, smaller eddies, swirling pools that spin off the main flow and live their own short lives before fading back in. The conveyor passes through all of this, brushing against each neighbor, trading a little heat here, a little salt there. The atmosphere is the loudest neighbor of all. Wind pushes the surface of the sea. Rain freshens it. Evaporation thickens it with salt. Every storm that crosses the ocean leaves a small fingerprint on the water below. Some of those fingerprints sink with the cold plunges near the poles and ride the conveyor for centuries. In a sense, the deep ocean is the long memory of the sky. The ice is another neighbor, and a strange one. Sea ice forms each winter at the poles, and when it freezes, it pushes salt out into the water beneath it. That salty water grows heavy and sinks, helping to feed the belt. So the ice and the conveyor are partners in a slow, quiet dance. If the ice changes, the dance changes too. Just how much and how quickly is one of the questions researchers are still trying to answer. Even the land plays a role. Rivers carry fresh water from continents into the sea, lightening the surface in some places and shifting where the heavy water can form. The shape of the sea floor steers the deep currents, funneling them through gaps between underwater mountains. The conveyor is not a free-floating ribbon. It is pressed and guided by every coastline and ridge it passes. There are theories about how tightly all these neighbors are linked. One idea is that the belt is fairly steady, recovering easily when one part of the system shifts. Another idea is that the belt is delicate, balanced on a knife edge, and that a small change in one place could ripple through the whole loop. The evidence is mixed. Sediment cores from the sea floor seem to show times when the belt slowed sharply, and other times when it ran strong and smooth. Why it shifted and what tipped it remains uncertain. The 1,000-year figure itself is a soft number. Some water moves faster, some slower. A drop that takes a shortcut through a warm western boundary current may finish its loop in less time. A drop that gets trapped in a deep basin near Antarctica may linger far longer, almost forgotten. The conveyor is not a single belt at all, but a tangle of overlapping paths, each with its own pace. What we can say is that the loop is long, longer than any human life, longer than most things humans build. The water moving through it carries the breath of ancient winters and the warmth of ancient summers, mixed and folded and slowly carried forward. Whether that great slow loop is steady or fragile or already changing under our feet is something the deep has not yet told us. It keeps its own time, and it does not seem to be in any hurry to share its answer. Of all the things the great ocean belt does, none feels stranger than its quiet talent for moving heat. The numbers, when you sit with them, are hard to picture. The belt and its surface partners carry something close to a quadrillion watts of heat from the warm middle of the planet toward the cold ends. That is a 1 followed by 15 zeros, expressed in watts. It is more energy than every power plant ever built by human hands, flowing without a single moving part, driven only by salt and cold and the slow turning of the world. Think of where this heat is gathered. Near the equator, the sun stands almost straight overhead for much of the year. The sea there can warm to nearly 30 degrees Celsius at the surface, the color of it deep and bright, like sapphire poured into a wide blue bowl. Water holds heat far better than air. A single thin layer of the upper ocean, only a few meters deep, stores more warmth than the entire atmosphere above it. The The tropics are, in a sense, a vast, slow boiler, gathering sunlight day after day, century after century, with nothing in particular to do with all that energy. The belt gives it somewhere to go. Warm surface currents peel away from the equator and drift toward higher latitudes, carrying that stored heat the way a kettle carries steam. The Gulf Stream alone, that famous warm river along the eastern edge of North America, moves more water than every river on Earth combined, many times over. Some estimates put its flow near 30 million cubic meters every second at its peak. Stand on a quiet shore and try to imagine that volume sliding past you, invisible, warm to the touch, carrying the memory of Caribbean sunlight toward the gray seas of the north. At the other end of the journey, the extremes flip. In the Greenland Sea and the Labrador Sea, in the long winter night, the surface water can chill below the freezing point of fresh water and still remain liquid, held just barely fluid by its salt. Around Antarctica, in the dark months, the surface of the sea grows skins of ice that thicken and crack and thicken again. The water beneath those ice shelves is some of the coldest liquid water anywhere in the natural world, hovering near -2 degrees Celsius. The belt drinks in this cold, pulls it downward, and sets it walking across the floor of the planet. The temperature gap between where the belt gathers heat and where it gives it up is, in places, more than 30 degrees Celsius. That difference is the engine. Without it, the belt would slow and possibly stop. With it, the tropics are kept from cooking, and the poles are kept from freezing solid. The whole arrangement is a slow act of balance, a quiet evening out of extremes that the sun alone would never manage. There are records hidden in this flow that still surprise the people who study it. The deepest cold water in the global belt, formed off Antarctica, can sit on the sea floor for more than 1,000 years before it sees daylight again. Some parcels of water in the deep Pacific have not touched the surface since long before any cities stood on any continent. They are, in a sense, the oldest weather on Earth, drifting under the keels of ships that have no idea they are there. The fastest parts of the belt are the surface currents, racing along at 2 meters per second in places, brisk as a walking pace. The slowest parts, deep in the abyss, creep at less than a centimeter per second, slower than the minute hand of a clock. The belt is both sprint and crawl at once, a single circulation that contains its own opposites. How exactly all of this heat budget will hold together as the planet warms is one of the open questions that researchers keep returning to. Some models suggest the belt will weaken, sending less warmth poleward. Others suggest the pattern will shift in ways that are harder to picture. The tropics may store more energy. The poles may receive it differently. The numbers are still being measured, the instruments still being refined, and the answers are not yet in. For now, the belt carries on its old work, gathering sunlight in one hemisphere and releasing it in another. The largest heating system the world has ever known, running silently beneath every ship, every coastline, every sleeping continent, in a balance that may be more delicate than it looks. Of all the threads woven into the Great Loop, the Gulf Stream is the one we know best, and yet it still holds quiet secrets. It begins in the warm shallows of the Caribbean and the Gulf of Mexico, where the sun has spent months pouring heat into the surface water. That heat does not stay still. It gathers into a moving band of warm, salty water that slips between Cuba and Florida, then sweeps north along the eastern edge of the United States. From space, satellites can see it as a ribbon of slightly darker blue, edged with swirls and curls, drifting against the cooler shelf water beside it. The ribbon is not narrow in the way a river on land is narrow. It can be 50 to 100 miles wide and more than half a mile deep in places. It carries more water than every river on Earth combined, many times over. And yet, standing on a beach in Florida, you would never see it. It runs offshore, beyond the breakers, a quiet giant moving past while gulls cry above the dunes. Up close, the Gulf Stream has textures that most people never hear about. Its edges fray into spinning eddies, round pockets of warm water that pinch off and drift away on their own. These eddies can be 100 miles across. They rotate slowly, like lazy wheels, sometimes lasting for months before they fade. Inside each one, the water is warmer and saltier than the sea around it. And tiny creatures gather there in patterns scientists are still mapping. Some eddies sink a little as they age, carrying their warm cores deep below the cooler surface, hiding pockets of tropical water far from the tropics. The boundary between the stream and the colder water beside it is also strangely sharp. In some places, you can cross a line in the sea where the temperature jumps by several degrees in just a few feet. Sailors have written about it for centuries, noticing how the color of the water changes, how the air above feels different, how fog can form along the edge where warm water meets cold. Benjamin Franklin, in the 1700s, helped sketch one of the first maps of the stream after talking with whaling captains who knew its path by heart. Their charts were rough, but the shape was already there. As the stream pushes north past Cape Hatteras, it leaves the coast and begins to wander out into the open Atlantic. Here it loses its tight shape and spreads into a slower, broader drift. Some of its water peels off and curls south. Some of it keeps moving northeast, carrying its warmth across thousands of miles of open sea. By the time it reaches the latitudes of Ireland and Norway, much of the heat it carried has already been released into the air above it, gently warming the winds that blow toward Europe. The small details are where the wonder lives. Tiny shifts in saltiness, just a fraction of a part per thousand, can change how the water sinks and where it goes. The shape of the seafloor below, ridges and canyons miles down, can nudge the stream slightly east or west. Even the spin of the earth itself bends the flow, pushing it to the right in the northern half of the world. Each of these forces is small on its own. Together, they sculpt the path of a current that helps decide whether winter in Dublin feels mild or harsh. Scientists still debate how steady this path really is. The Gulf Stream itself, the part that hugs the American coast, seems fairly reliable. But the slower drifted feeds into farther north, the part that delivers warmth to Europe, may be more delicate. Some measurements suggest that this northern extension has shifted in recent decades. Others suggest the changes are within the normal range of natural wobble. The honest answer is that we do not yet have enough long records to be sure. ocean currents move slowly, and our instruments have only been listening in any careful way for a few decades. There are quiet beauties hidden in this uncertainty. The thought that a warm sip of water leaving the coast of Florida might, years from now, brush against a fishing boat off the coast of Scotland. The idea that every gentle winter evening in a small European village owes something to a sun that warmed a sea on the other side of the world. The full picture is still being drawn. For tonight, it is enough to picture that wide blue ribbon drifting north under the stars, carrying its warmth somewhere we cannot quite see. For a long time, sailors knew something strange about the western edge of Europe. In the deep of winter, the harbors of Norway often stayed open, while ports much farther south in Canada froze solid. Towns in Scotland and Ireland kept gardens green through January. Palm trees grew on a few sheltered coasts in the far west of the British Isles. The latitude said one thing, the weather said another. Early map makers noticed the puzzle, but had no clear answer. They could draw lines of latitude across the globe and see that London sat as far north as the middle of Hudson Bay. They could see that Bergen, on the coast of Norway, sat above the level of Anchorage in Alaska. Yet the cold of those western places never matched. Something warm seemed to lean against the European coast and refuse to leave. The first careful steps toward understanding came from sea captains who kept journals of wind and water. They wrote down the temperature of the sea each day. They watched the colors of the water shift from gray to a deep, glassy blue. They felt the air grow softer as their ships drifted into certain bands of ocean. Many of them suspected they were crossing a kind of river inside the sea, though they had no name for it. In the 18th century, a curious thinker named Benjamin Franklin began collecting these observations. He had noticed that mail ships sailing west from England took far longer than the same ships heading east. Sailors told him about a warm, fast band of water flowing up from the tropics. Franklin worked with a cousin who was a whaling captain, and together they drew one of the first useful charts of this current. The chart showed a wide ribbon of warm water sweeping up the American coast, then bending across the Atlantic toward Europe. For a while, people thought this warm ribbon alone was the secret. The current carried heat from the Caribbean, the thinking went, and that heat warmed the air over Europe. It was a simple, satisfying picture. The mild winters of Britain, France, and Norway seemed to have a clear cause at last. Over time, the picture grew more complicated. Other scientists measured the strength of the winds that blow across the Atlantic from west to east. They found that those winds also carry heat picked up from the sea surface and deliver it to the European coast. Some researchers began to argue that the winds did most of the work, and the current did less than Franklin's chart suggested. The debate has never fully settled. Today, many scientists believe both the current and the winds matter, and that the two systems lean on each other in ways that are still being studied. Then came a deeper realization. The warm surface flow was only one piece of something much larger. In the late 20th century, an oceanographer named Wallace Broker began describing a single connected loop that stretched through every ocean. He sketched it on paper as a long ribbon, sinking near Greenland, drifting along the deep sea floor, rising again in distant waters, and returning to the surface to begin once more. He gave it a simple name. He called it the Great Ocean Conveyor. That image changed how people thought about Europe's mild winters. The warm water lapping at the coasts of Ireland and Norway was not just a local current. It was the surface arm of a planet-wide loop. The heat being delivered to Europe had been gathered from tropical seas far away, lifted northward, and finally released into the cold air above the North Atlantic. After giving up its warmth, that same water grew dense and sank, beginning the long underwater leg of its travel. Even now, the full picture remains incomplete. Scientists still debate exactly how much of Europe's winter warmth comes from the deep conveyor. How much comes from the surface current alone, and how much comes from the steady push of the winds. Computer models give different answers depending on how they are built. Some suggest the conveyor is the main reason. Others suggest the winds matter more, and the conveyor adds only a gentle extra warmth on top. What the early sailors felt on their skin, and what Franklin drew on his old chart, has grown into one of the most studied questions in ocean science. The mystery has not closed. It has only deepened. Each new measurement seems to reveal another layer, another connection, another thread tying the warmth of a Scottish garden to the salt of a sinking sea 1,000 miles to the north. The question of why Western Europe stays mild remains a quiet puzzle, still being slowly solved. The monsoons feel like creatures of the sky. Great walls of cloud, warm rain falling on rice fields, the dry months breaking at last into a hush of water. They seem like a story written in the air, in the heat of the sun and the tilt of the land. And yet, when you follow the threads back far enough, many of those threads lead down into the sea, down into the slow walking of the conveyor belt, far below the waves. This is one of the surprises that even careful researchers still find strange. The rains that soak a village in India, or the dry season that bakes the soil in West Africa, may carry within them the memory of water that sank in the cold north many years before. The ocean and the sky are not separate stages. They are one slow machine, breathing in and out across centuries. The idea sounds almost too large to hold. A farmer in the Sahel watches the clouds gather, or fail to gather, and the cause may lie in the saltiness of a sea he will never see. The conveyor belt carries heat into the North Atlantic. That heat shapes the air above it. The air above the Atlantic helps decide where the rain bands sit over Africa. Move the heat a little north, the rains move north. Move the heat a little south, the rains follow. Whole harvests rest on the position of a band of cloud, and the band of cloud rests, in part, on a current few of us can picture. Some researchers have spent careers trying to read this connection. They look at old climate records, at the layers of mud in African lakes, at the rings in cave stone. They find that when the northern ocean grew colder in the past, the African monsoon often weakened, and the green parts of the Sahel pulled south. When the northern ocean warmed, the rains pushed north again, and grasses spread where sand had been. The pattern is striking. The exact mechanism, though, is still being argued. One idea is that the heat balance between the two hemispheres tugs the tropical rain bands like a slow pendulum. Another idea points to changes in the winds first, with the ocean responding rather than leading. The truth is probably a braid of both, and no one has untangled it fully. The Asian monsoon adds its own puzzle. Each summer, the land of Asia heats faster than the sea around it, and moist air sweeps inland from the Indian Ocean. The rains come, and a continent drinks. But the strength of those rains seems to flicker with the long ocean cycles too. Some studies suggest that when the conveyor belt slows in the Atlantic, the Asian monsoon weakens in response, half a world away. Other studies see the link as smaller or filtered through many other forces. The signal is real. The size of it is still open. Even the rains over South America seem to listen. The wet season in parts of the Amazon and the dry corridors that run beside it shift gently as the Atlantic shifts. Cores of mud pulled from old lake beds in Brazil show wet times and dry times that line up, more or less, with cold and warm spells in the northern sea. The fit is not perfect. Climate is never that tidy, but the pattern keeps appearing in record after record until it becomes hard to ignore. What makes all of this strange is the delay. The conveyor belt is slow. A parcel of water sinking near Greenland may not return to the surface for hundreds of years. So the rain that falls tonight on a hillside in Asia may, in some small part, be answering a chill that touched the North Atlantic long before any of us were born. The sky has a memory. It did not write itself. It borrows that memory from the sea. Researchers are still asking how much of the monsoon is shaped by the ocean and how much by the land and the winds alone. They build models, run them, compare them to ancient records, and adjust. The models agree on the broad shape of the link. They disagree on the details, on the strength, on which way the influence flows in any given season. The question stays open, and the open part is the interesting part. For tonight, it is enough to hold the picture in mind. A monsoon rain falling on warm stones. A river of cold water creeping along the sea floor in the dark. The two of them somehow listening to each other across the long quiet of the world. There is a quiet thread that ties the great desert of the Sahara to the green heart of the Amazon. Each year, winds lift fine dust from a dry lake bed in northern Chad. That dust rises into the sky, sometimes climbing for miles above the dunes. Then it travels west, across the whole width of the Atlantic, riding the trade winds like a thin orange veil. When the dust finally falls, much of it lands on the rainforest of South America. The Amazon soil is old and washed thin by constant rain, so it lacks certain minerals the trees need. Scientists believe that the iron and phosphorus in that desert dust may help feed the forest. One quiet desert, half a world away, may be helping the largest rainforest on Earth stay green. The conveyor belt sits beneath all of this, shaping the winds that carry the dust. The warm surface flow heading North Pole's air patterns with it. The cold, deep return helps set where rain falls and where the sky stays dry. The Sahara itself may exist, in part, because of how the great currents push moisture toward some lands and away from others. The forest and the desert are not strangers. They are partners in a much wider system, joined by water and wind and ocean. The sun is the silent engine behind all of it. Sunlight strikes the tropics most directly, warming the surface water there. That warmth is what the belt carries north, and what the belt brings back as cold from the poles. Without the sun's uneven touch on a round planet, there would be no temperature gap to drive the flow. The conveyor is, in a sense, the ocean's slow answer to the sun's uneven gift. Volcanoes play a part too, in ways still being studied. When a large volcano erupts, it can send fine ash and tiny droplets of sulfur high into the upper air. These particles reflect a little sunlight back into space and cool the surface for a year or two. A cooler surface changes how much ice forms near the poles. More ice means more salty water sinking, which may, in turn, nudge the belt to flow a little faster. Some researchers wonder if past bursts of volcanic activity gave the conveyor small shoves across long stretches of history. Others think the effect is weaker than that. The question stays open. Even the moon joins the symphony. The tides it pulls across the ocean help mix deep water with shallow water. Without that mixing, cold bottom water might just sit, heavy and still, with nowhere to rise. The moon's gentle tug, repeated for billions of years, may help keep the loop alive. How much it matters compared to wind and salinity is still debated, and the numbers are hard to pin down. The atmosphere and the ocean trade gases as well. Carbon dioxide breathes in and out of the sea surface, and cold water holds more of it than warm water. When the belt drags cold, gas-rich water down into the deep, it locks carbon away for hundreds of years. When that same water rises again in the Pacific, some of the carbon returns to the sky. The forest above breathes it in. The ocean below holds it. The desert sends its dust. Each piece moves at its own pace, and yet the pieces seem to know one another. Even galaxies may have a faint say in all this. Our solar system drifts through the Milky Way, passing through regions where cosmic rays, tiny, fast particles from deep space, are more or less common. Some scientists wonder if these particles help seed cloud droplets in the upper air. More clouds would mean a cooler ocean surface, and a cooler surface could shift where the belt sinks and rises. The idea is not settled. The signal, if it exists, is very small. Still, it hints that the conveyor may feel echoes from far beyond the sky. What seems clear is that the belt does not act alone. It is one voice in a long, slow song. The sun pours heat. The wind drags the surface. The rivers pour fresh water in. The ice grows and melts at the poles. The forests breathe. The deserts send their dust across the sea. The moon pulls. The volcanoes whisper their cooling breath. And somewhere in the middle of all of it, a slow river of water carries warmth from one side of the world to the other. How tightly all these threads are woven, and how much one can change without changing the rest, remains an open question. For now, the symphony plays on, mostly out of sight. The belt is old, older than any city, older than any forest, older than any story ever told around a fire. And the belt remembers. Locked inside its slow waters, and inside the cold mud at the bottom of the sea, there are quiet hints of what the belt has done before. Hints that it has not always moved this way. Hints that, in the deep past, it has slowed, shifted, perhaps even paused. mystery of how the belt changes over long stretches of time is one of the gentler puzzles in Earth science. And it is a puzzle we are still trying to read. Scientists drill long tubes of mud from the deep ocean floor. These tubes are called sediment cores. Each layer in the mud holds tiny shells, grains of dust, and chemical traces from a different age. By reading these layers, researchers can sketch a rough picture of what the ocean was doing thousands, even millions of years ago. The shells of small sea creatures hold clues about water temperature. The dust holds clues about distant winds, and the patterns in the layers seem to whisper that the belt has changed many times. During the great ice ages, when thick sheets of ice covered much of the northern world, the belt may have moved very differently. Some researchers believe the northern plunge weakened or shifted south, or perhaps stopped for long stretches. Other researchers think the belt kept flowing, but along altered paths, fed by different sources of cold, salty water. The full story remains open. The mud tells us something happened. It does not always tell us exactly what. One idea that has gathered interest is that fresh meltwater from collapsing ice sheets once poured into the North Atlantic in huge pulses. Fresh water is lighter than salty water. If enough fresh water spread across the northern seas, it could have made the surface too light to sink. And if the surface could not sink, the engine of the belt might have slowed. Some researchers think this happened more than once. Others wonder whether the slowdown was the cause of sudden climate shifts seen in the ice record, or only one piece of a larger puzzle. There is a famous chapter in this story called the Younger Dryas. Around 12,000 years ago, as the last ice age was ending, the climate of the North Atlantic seemed to flip back into deep cold for about 1,000 years. Winters returned, forests retreated. Then, almost as quickly, the warmth came back. Many researchers suspect the belt was involved. Perhaps a great surge of meltwater hushed the northern plunge. Perhaps the belt rerouted itself. The exact chain of cause and effect is still debated, and the evidence is still being gathered, one mud core at a time. Even further back, the belt may have looked very different, when the continents themselves were in different places when the Isthmus of Panama had not yet closed, when the gateways between oceans were wider or narrower, the Great Loop took other shapes. The ocean has worn many faces. The current pattern, with its long northern plunge and its slow Pacific climb, is only one configuration in a very long history. We do not know how many other configurations there have been. We do not know which were stable for long stretches and which were brief experiments. What we can say gently is that the belt is not a fixed machine. It is more like a slow, breathing creature. It speeds, it slows, it shifts its path by small degrees. Over a human life, these changes are nearly invisible. Over centuries, they leave faint marks in the mud. Over many thousands of years, they help shape ice ages and warm ages, deserts and rainforests, the rise and fall of vast climate patterns we are only beginning to understand. And the belt is changing right now, in this very moment, in ways we cannot fully see. Fresh water is once again entering the North Atlantic, this time from melting ice in Greenland. The waters of the deep are slowly shifting. Some measurements suggest a small weakening. Other measurements remain uncertain. Researchers do not yet agree on how much, or how fast, or what it means for the coming centuries. The belt is doing what it has always done. It is responding. It is adjusting. It is keeping its own quiet record of the world above. So as you rest, consider the mud at the bottom of the sea, holding pages of an unfinished book. A book the ocean has been writing for millions of years. A book we are only just learning to read. Light is how we read the ocean from far away. Satellites drift above the earth, watching the surface in many colors. They measure the height of the water, the warmth of it, the faint blue and green tints that hint at life below. From this gentle light, scientists try to learn whether the Great Conveyor Belt is still flowing as strongly as it once did. The signal they look for is strange and quiet. It is a patch of ocean in the North Atlantic, south of Greenland and Iceland, that has been growing slowly cooler while the rest of the world grows warmer. Some researchers call it the cold blob. In maps of sea surface temperature, where most of the planet glows in warm reds and oranges, this patch stays a steady, soft blue. it is the only part of the ocean that seems to be cooling in this way. One idea is that the cold blob is a kind of fingerprint. If the conveyor belt is slowing, less warm water from the south would reach the far north. The surface there would cool, even as the rest of the world warmed. The light coming off that patch of sea would tell the story of a current losing its strength. Some studies of ocean records going back more than a century suggest that the flow may already be weaker than it was 1,000 years ago. The evidence is gathered from many sources, and the picture is still blurry. Other researchers are more cautious. They point out that the ocean is a noisy place. Natural cycles can cool one patch of water for decades and then warm it again. The cold blob might be a sign of a slowing conveyor, or it might be a slower, gentler rhythm that has nothing to do with the deep current at all. The light tells us something is different there, but it does not yet tell us exactly why. To learn more, scientists turn to other kinds of light. Floating robots, called Argo floats, drift through the deep ocean and rise to the surface every few days. When they reach the top, they send their data up to satellites using radio waves, which are a form of light invisible to our eyes. In this way, the deep ocean speaks to space, and space passes the message back to scientists on land. From these whispers, researchers piece together how the layers of the sea are shifting. The story they read is complicated. In some years, the deep flow near Greenland seems stronger. In other years, it seems weaker. Measurements taken along a line of moorings stretched across the Atlantic, near the latitude of Florida and Morocco, show the conveyor wobbling like a slow heartbeat. There are seasons of vigor and seasons of rest. Whether the long-term trend points downward is still debated among the scientists who watch these numbers most closely. There is another kind of light that matters here, and it shines on the ice. The great ice sheet of Greenland reflects sunlight back into space, a quality known as albedo. As the ice melts, more dark water and dark rock are exposed, and more sunlight is absorbed. The melted water, fresh and cold, slides into the sea around Greenland and spreads across the surface. Fresh water is lighter than salty water, so it tends to float. Some researchers wonder if this layer of fresh water could be making it harder for the surface to sink in the places where the conveyor begins. That would be the kind of slow change a satellite might catch only over many years. The light from the cold blob, the faint shimmer of meltwater along the Greenland coast, the slow shifting of currents along the edge of the ice. All of these are clues. None of them on their own can answer the question. Together, they form a picture that is suggestive but not certain. So the conveyor may be slowing, or it may be moving through one of its natural, quiet phases, or the patterns we see may be a mixture of both, tangled together in ways we cannot yet untangle. The light tells us where to look. It does not yet tell us what we will find. For tonight, it is enough to imagine that pale blue patch of sea, glowing softly under a gray northern sky. The water there is cooler than it should be, and no one is entirely sure why. Far below it, the deep current is doing what it has done for thousands of years, slipping southward through the dark. Whether its pace is steady or fading, the ocean keeps its secret a little longer beneath the changing light. On the floor of the deep ocean, in the dark places where the conveyor belt drifts slowly past, there is a soft and ancient layer of mud. This mud is not silent. If you could press a careful ear against it, or send down the right instrument, you would find a quiet record of everything the current has ever done. Each grain holds a small memory. Each layer is a page in a book that took millions of years to write. The mud is made of tiny shells. Long ago, near the sunlit surface, single-celled creatures grew thin homes of chalk and glass. When they died, their shells drifted down through the cold dark, falling like a slow and endless snow. Layer by layer, these shells settled into the sea floor. The deeper you dig, the older the snow becomes. Some of the mud at the bottom of the Atlantic fell during the time of the last ice age. Some of it fell long before that. Researchers who study this mud listen to it in a strange way. They lower long hollow tubes into the sediment and pull up cores, columns of soft earth that look like striped candles. Within each core, the layers tell a story about the water that once passed over them. Cold water leaves one kind of signal. Warm water leaves another. Fast currents stir the grains and sort them by size. Slow currents let the finest dust settle in peace. The sound, in a sense, is the quiet hum of all that falling and settling. It is the soft clatter of microscopic shells touching down on a bed of older shells. It is the gentle drag of bottom water sweeping the grains into shapes you cannot see from above. The sea floor under the conveyor belt is not flat. It carries long ridges and ripples carved by the current, the same way wind carves dunes in a desert. If you could speed up time and listen, you might hear something like a long, slow breath drawn in and pushed out over thousands of years. What the mud seems to whisper is that the conveyor belt has changed before. In some cores, the layers shift suddenly. The shells from cold-loving creatures appear where warm-loving creatures used to live. The chemistry of the grains tells of water that came from a different direction, or paused, or thinned to a trickle. Many researchers believe these shifts match moments in Earth's deep past when the climate jolted from one state to another. One idea is that the belt slowed or even stopped and then began again much later. The story is not simple, though. The mud is patient, but it is also imperfect. Worms tunnel through it. Bottom currents sometimes scrub away whole pages. Different cores from different parts of the ocean do not always agree. One core may suggest the belt weakened sharply. Another, taken not far away, may suggest a gentler change. Some researchers wonder whether the signals come from the current itself or from changes in the surface water far above, or from shifts in the winds. The question of what exactly the mud is telling us remains open. There are other sounds woven into this record. Layers of fine ash mark old volcanic eruptions. Pale bands of dust mark dry centuries when winds carried the Sahara out over the sea. Dark bands mark times when the deep water held little oxygen and life on the bottom grew thin. Each of these signals overlaps with the others. Pulling them apart is slow, careful work, and reasonable researchers can read the same core in more than one way. What seems clear is that the conveyor belt does not run at a single steady pace forever. The mud suggests it speeds up and slows down, shifts its path, and and sometimes falters. What is not clear is how often this happens, how fast it can happen, or what truly triggers it. Some cores hint at changes that took centuries. Others hint at changes that took only decades. The difference matters, but the evidence is still incomplete. So the sound of this section is not a roar or a crash. It is the soft, papery rustle of shells settling into mud. It is the slow scrape of bottom water across an ancient plain. It is the patient turning of pages in a book no one has finished reading. Somewhere down there, in the cold dark, the conveyor belt is still writing its next line. We do not yet know what that line will say, or how it will compare to the lines that came before. The mud keeps its own quiet counsel, and we are only beginning to learn its language. The mathematics of the Great Conveyor Belt is, at its heart, a story about balance. Cold water sinks because it is dense. Salty water sinks because it is dense. When water is both cold and salty, it grows heavy enough to fall through the lighter water beneath it. That single rule, repeated across millions of square miles of sea, sets the whole loop in motion. The numbers behind it are not flashy. They are quiet, and they are exact. In the far north, surface water cools to near freezing. Its saltiness rises as ice forms above it, since ice locks away fresh water and leaves the salt behind. The density of that chilled, salty water climbs by only a tiny fraction, a few parts in 1,000. That is enough. The water tips downward and begins its slow, sinking walk into the deep. From such a small change, an ocean-wide engine takes its first breath. Researchers who study this engine often speak of a single number that tries to summarize the entire flow. They call it the strength of the overturning, measured in a unit named the sverdrup. One sverdrup is 1,000,000 cubic meters of water moving every second. The Atlantic limb of the conveyor is thought to carry somewhere between 15 and 20 sverdrups in modern times. That is more than all the rivers of the world combined, many times over, flowing in a single slow direction through the dark. The mathematics grows interesting when scientists try to ask what happens if that number drops. If 15 sverdrups become 10, the climate of the North Atlantic shifts. If 10 become 5, the shift grows larger. And somewhere in those numbers, there may be a point where the system does not simply slow. It may, in theory, switch off. This is the question of a sudden shutdown, and it is one of the most carefully studied open questions in ocean science. The idea rests on a branch of math that studies systems with more than one stable state. A pencil balanced on its tip has one resting state on each side. A small push moves it gently. A large push tips it over, and it does not return. Some ocean models suggest the conveyor may behave a little like that pencil. It may have a strong state where the loop runs as it does today, and a weak state where the northern sinking nearly stops. Between those two states sits a threshold. Cross it, and the system does not drift back on its own. What might push the pencil over is fresh water. Rain, melting ice, and rivers all add fresh water to the surface of the northern seas. Fresh water is lighter than salty water. If enough of it spreads across the sinking regions, the surface may grow too light to fall. The downward plunge weakens. The loop loses its pull. In some models, this happens slowly over centuries. In others, it happens within a few decades once the threshold is crossed. The math allows both outcomes, depending on the assumptions inside the model. This is where the open question lives. No one knows where the threshold actually sits. No one knows whether the real ocean behaves like the simple equations or like something more forgiving. Some studies suggest the modern flow is already drifting toward a weaker state. Other studies suggest the system is more stable than the early models implied, and that a full shutdown remains unlikely within any human lifetime. The numbers disagree because the ocean is enormous and the measurements are young. We have only been watching the deep flow with care for a few short decades. There is a strange beauty in this uncertainty. The equations are simple. Density, gravity, salt, temperature. A schoolchild could grasp the basic rules in a single afternoon. And yet, when those rules are applied to a planet wrapped in water, they produce behavior that the sharpest minds cannot fully predict. The system is simple in its parts and deeply complex in its whole. That is often how the universe seems to work. Small rules, vast consequences, a handful of constants that shape the weather on every coastline. So the mathematics leaves us with a quiet question rather than an answer. Somewhere in the cold north, salty water is sinking tonight. It is sinking at a rate that can be written as a number, though that number wavers slightly from year to year. Whether it will keep sinking at this pace for another century, or whether it will one day pause, remains unresolved. The equations whisper of two possible worlds. The ocean, for now, has not told us which one it intends to choose. Imagine for a quiet moment what the world might look like if the Great Conveyor Belt slowed to a crawl or stopped altogether. No one knows for certain what would happen. The ocean has done this before, deep in the past, and the planet seems to have shifted in response. But the exact picture remains blurry, sketched in by computer models and by clues buried in old layers of mud. One leading idea is that without the northern plunge, less warm water would flow up from the tropics into the North Atlantic. The seas around Iceland, Greenland, and northern Europe would slowly cool. Winters could grow longer. Sea ice might spread farther south than it has in many centuries. The mild, damp air that brushes the coasts of Ireland and Norway could grow sharper, drier, more biting. Some models suggest the change could unfold over decades. Others suggest it could take much longer. The honest answer is that we do not yet know. A second idea is that the tropics themselves would feel the shift. Heat normally carried north would pile up near the equator. The rain belts that feed the monsoons could wander. Some regions might grow wetter, others much drier. The Amazon, the Sahel, the rice fields of southern Asia all sit within reach of these moving bands of moisture. A small nudge in the ocean might mean a large change in the sky above a distant continent. Whether this would happen quickly or gradually is still debated. A third possibility raised by some researchers is that the southern half of the planet might warm while the north cools. Heat that once traveled across the equator would linger in the Southern Ocean instead. The ice around Antarctica could respond in ways that are hard to predict. This idea is called the seesaw, and traces of it appear in ancient ice cores. But whether a future slowdown would mirror those ancient patterns is far from settled. What strikes many who study these questions is how thin the margin seems. The belt depends on water that is just salty enough, just cold enough, just dense enough to sink in a few small patches of the northern sea. Change the saltiness a little, and the sinking weakens. Change the temperature a little, and the same. The engine that helps steer the weather of every continent runs on a difference of a few degrees and a few grams of salt per liter. It is a strange thing to consider, lying in the dark. And the belt is only one delicate piece. The whole planet seems built on quiet balances. The atmosphere is a thin shell, no thicker in proportion than the skin of an apple. It holds in warmth, filters harsh light, and lets rain fall in patterns that life has come to expect. The earth sits at a distance from the sun, where water can be liquid across most of its surface. A little closer, and the oceans might boil away. A little farther, and they might freeze solid. The tilt of the axis gives us seasons. The moon steadies that tilt across long ages. Each of these settings sits within a narrow range. None of this means the planet is fragile in the sense of breaking easily. Earth has weathered ice ages, asteroid strikes, vast volcanic outpourings, and changes in the sun's brightness. Life has bent and adapted. But the particular climate we know, the one in which our cities and farms and forests sit comfortably, may rest on a narrower set of conditions than the deeper history of the planet. The conveyor belt is part of that comfort. Researchers wonder then what a world without the belt would feel like to those living through it. Some imagine slow, almost unnoticed change year by year, until old maps no longer match the weather. Others imagine sharper shifts, where a season arrives unexpectedly cold or unexpectedly wet, and patterns that held for generations quietly come undone. The truth, if we ever see it, may lie somewhere between, or somewhere else entirely. For now, the belt still turns. Cold water still sinks in the Greenland Sea. Warm water still drifts north along the edges of continents. The Gulf Stream still carries its hidden heat toward Europe. still falls on the Amazon in the rhythms it has known for thousands of years. The system holds, and the question of how delicately it holds remains open. It is a strange comfort, in a way, to think of all these careful balances working together in the dark, keeping the windows of your room a familiar temperature, keeping the night outside soft enough to sleep in. For all its scale and slow grandeur, the Great Conveyor Belt of Earth's oceans may not be the only one of its kind. Out beyond our own warm seas, there are other oceans, hidden ones, oceans we cannot see from any telescope, oceans tucked under thick shells of ice on the cold moons of the outer solar system. And the question that drifts through quiet laboratories and long planning meetings is a soft and patient one. Do those buried seas have currents too? Do they have their own slow rivers in the dark? We do not know yet. That is the honest answer. But the clues are there, faint and inviting, like footprints in deep snow. Consider Europa, a small moon that circles Jupiter. Beneath its bright, cracked shell of ice lies what most researchers believe is a salty ocean, possibly twice the volume of all the water on Earth. The surface is pale and scored with long reddish lines, as if something below has been pressing up and pulling apart for ages. The water beneath that shell never sees sunlight. It sits in eternal darkness, warmed not by a sun, but by the slow squeeze of Jupiter's gravity, kneading the moon like soft clay. If that ocean is real, and most evidence suggests it is, then the same simple ingredients that drive our own great conveyor may live there too. Warm water rising, cold water sinking, salt changing the weight of one parcel against another. One idea is that Europa's ocean has its own slow circulation, with warm plumes drifting up from the rocky floor and cool water sliding back down along the underside of the ice. Another idea suggests the flow may be far more chaotic, with swirling eddies and no steady belt at all. The truth waits beneath the ice, unbothered by our guessing. Enceladus, a tiny moon of Saturn, gives us another whisper. From its southern pole, long plumes of water vapor and ice grains shoot into space through cracks in the surface. Some of those grains carry salts, and simple organic molecules. That tells us the ocean below is real, salty, and in contact with warm rock. But does it circulate? Does cold water near the icy roof sink? Does warm water at the seafloor rise and travel? Some researchers wonder if Enceladus has a small, quiet conveyor of its own, looping slowly between pole and equator. Others suspect its ocean may be too small and too oddly shaped to form a steady pattern. The question remains open. Then there is Titan, another moon of Saturn, which carries something stranger still. On its surface, under an orange haze, there are lakes and seas, but they are not made of water. They are made of liquid methane and ethane, cold hydrocarbons that flow like gasoline. Titan may also hide a deeper water ocean far beneath its crust. So Titan may have two layered seas, each with its own possible motion. Whether the methane lakes have tides and currents of their own, driven by Saturn's pull, and Titan's slow winds, is a puzzle scientists are still piecing together. Early measurements hint at gentle flows, but the picture is incomplete. Even Ganymede, the largest moon in the solar system, may carry a hidden ocean sandwiched between layers of ice. The pressures down there would be strange, the temperatures barely above freezing, and the chemistry unfamiliar. A current in such a place would not look like our Gulf Stream. It might be slower, quieter, stranger. Or it might not exist at all. What makes all of this so soothing to consider is how much we still get to learn. Our own Great Belt took centuries of patient measurement to even begin to understand, and we live right next to it. The oceans of other worlds are far away, sealed under miles of ice, and yet we are slowly finding ways to listen for them. Future missions hope to fly through the plumes of Enceladus and taste their contents more carefully. Other missions plan to orbit Europa and map the thickness of its shell. None of them will pull back the ice and show us the currents directly, but each will add another small clue. And the open question lingers: if the engines that drive our weather, our climate, our long balance of warmth and cold, also turn somewhere beneath the ice of distant moons, then the idea of an ocean conveyor may not belong to Earth alone. It may be a pattern the universe likes to repeat. Wherever liquid and heat and salt can meet in the dark. For now, we listen. We wait. We imagine slow rivers in places no light has ever touched. Far below the surface, where sunlight has never reached, there are machines that listen. They drift in the cold dark, quietly noting the temperature of the water around them. They measure how salty it is. They feel the faint push of the current as it slides past their sensors. And every so often, they rise toward the surface and send a small signal up to a satellite, telling the world what they have found. These machines are called floats, and there are thousands of them now, spread across every ocean. Together, they form a kind of nervous system for the planet's water. Some sink to 2 kilometers down. Others go deeper, into the abyss where the conveyor belt does its slowest work. They are simple tools, really a tube, a battery, a few sensors, a bladder that swells and shrinks to change their depth. But together, they are giving us our first real picture of what the deep ocean is doing. There are other instruments too. Long cables stretched across the floor of the Atlantic, measuring the flow of water as it passes overhead. Anchored stations that hang in the current like underwater wind chimes, swaying with each pulse of the belt. Robotic gliders that slip silently through the water for months at a time, their wings adjusting to the slow drift. Each one adds a small piece to the puzzle. And yet, the puzzle is enormous. The ocean is so vast, and the conveyor moves so slowly that even thousands of instruments can only sketch the rough shape of it. The deep flows we most want to understand are also the hardest to reach. A single loop of the belt takes 1,000 years. To truly watch it change, we would need to listen for centuries. So researchers are building tools meant to last. New floats that can run for a decade on a single battery. Sensors that can survive the crushing pressure of the deepest trenches. Ideas for fleets of small robots that would patrol the polar seas, watching the cold water as it sinks. Some scientists imagine a future where the entire ocean is laced with quiet listeners, each one a tiny witness to a story too slow for any single human life to follow. What might these instruments tell us in 100 years? In 1,000? The honest answer is that we do not know. One possibility is that the belt will keep flowing much as it does now, and the records will simply grow richer and more detailed. Another possibility is that the flow will weaken, and the instruments will measure the slowing in real time, year by year. A third possibility is something stranger, a shift no one predicted, a new pattern that emerges only when we finally have enough data to see it. Look further out, and the questions stretch into deep time. In 1,000,000 years, the continents themselves will have moved. The Atlantic will be a little wider, the Pacific a little narrower. The doorways that let water pass between oceans may have shifted. The conveyor will still exist in some form, almost certainly, but its path may be different. The cold plunge in the north may happen in a slightly different sea. The slow climb in the Pacific may rise along a slightly different shore. In 100 million years, the map will be barely recognizable. Some researchers think the continents will gather again into a single great landmass, the way they did in the deep past. If that happens, the ocean will become one enormous basin, and the conveyor will have to find a new way to circulate within it. What that current would look like, no one can say with certainty. The models are only guesses, and the guesses depend on which way the continents drift. Further still, in 1 billion years, the sun will have grown brighter and warmer. The oceans themselves may begin to thin, slowly evaporating into a thicker sky. The belt may slow or stall or transform into something we have no word for. And eventually, in a future so distant it can barely be imagined, the water may be gone altogether, lifted away into space, leaving the seabed dry and silent under a redder sun. But that is so far ahead that it hardly feels real. For now, the instruments hum quietly in the dark. They rise, they sink, they whisper their findings to the satellites overhead. They are gathering the first long record of a current that has been turning for longer than our species has existed. What they will hear in the years to come, and what stories the deep water still has to tell, remain open questions drifting somewhere below the waves. Step back now, as far back as you can. Picture the whole earth hanging in the dark, a small blue marble in the quiet of space. The conveyor belt we have been wondering about for hours tonight is hidden inside that blue. It is the slow breath of the planet, moving water from pole to pole, carrying heat and salt and memory through every basin. From far enough away, you cannot see the belt at all. You only see the blue. And yet, that blue is something rare. We have searched the sky for water on other worlds. We have found ice on moons, traces of vapor in the air of distant planets, and oceans buried under frozen shells. But a wide, open, sunlit ocean, free to move and mix and breathe, seems to be unusual. Earth's surface holds more liquid water than any place we have yet confirmed. And inside that water, the belt turns. The atoms in that water are old. The hydrogen formed in the first minutes after the universe began. The oxygen was forged inside stars that lived and died long before the sun was born. When those stars ended, they scattered their cooked atoms into the dark. Some of those atoms drifted for billions of years before gathering into the cloud that became our solar system. Some of them settled into the young Earth. Some of them are in the ocean tonight, riding the belt, sliding past the coast of Africa, or sinking into the deep near Greenland. Every drop of seawater is, in this sense, ancient. The salt in it carries the slow weathering of continents that no longer exist. The water itself was forged in the bellies of dying stars. The current that moves it took shape only after the continents drifted into their present arrangement. Only after the gaps between them opened and closed in the right pattern. The belt is a young feature on an old world made of older atoms. And we are part of the same story. The calcium in your bones, the iron in your blood, the carbon in every cell. All of it was made in stars. You are, in a real sense, a small warm pocket of stardust, lying still in the dark, listening to a voice describe the ocean. The same kinds of atoms that move through the belt also move through you. The water in your body has cycled through clouds and rivers and seas, perhaps even through the belt itself, long before it ever became yours. So when we ask whether the belt will slow or shift or one day pause, we are asking a question about ourselves. The belt shapes the air that grows the food, that feeds the cells that think the thoughts. It is not a distant machine. It is part of the same quiet system we belong to. question stays open. We do not know exactly how stable the belt is. We do not know how close it might be to a turning point, or how far. We do not know whether it has slowed a little or a lot in recent decades, because our records are still short and the ocean is vast. Some studies suggest a gentle weakening. Others find the signal too small to be sure. The honest answer is that we are still learning to listen. We do not know whether other worlds have currents like ours. Under the ice of Europa, under the ice of Enceladus, water may be moving in slow, patient loops, stirred by heat from below instead of wind from above. If those loops exist, they would be hidden oceans with hidden weather, turning in the dark for ages without a single sunrise. Whether life rides those currents the way it rides ours is one of the great open questions of our time. For tonight, none of that needs an answer. The belt will keep turning while you sleep. Cold water will sink near Greenland. Warm water will drift north along familiar coasts. Salt will gather and disperse. Heat will move from the tropics toward the poles in a slow, steady walk that takes longer than any human life. You are made of the same stuff as the sea, and the stars beyond it. The mystery of the belt is part of the larger mystery of being here at all. On a small blue world, briefly awake, briefly wondering. Let the wondering settle now. Let the questions drift like cold water sinking into the quiet places where sleep gathers. The belt will keep its long, patient loop without you, and the universe will keep turning around it, ancient and unhurried in the dark. And so we come to the quiet end of our long, slow walk through the hidden river of the sea. We have followed the cold water as it sinks in the north, drifted with it through the dark Atlantic, watched it bend around the bottom of Africa, and felt it rise again in distant warm seas. We have asked what would happen if the belt slowed, what it remembers from the ice ages, and whether other worlds might hide their own quiet currents under sheets of ice. None of those questions have full answers tonight. None of them needed one. Picture for a moment the Earth from very far away. A small blue world turning slowly in the dark. From here you cannot see the storms or the cities or the ships. You can only see the soft swirl of white cloud and the deep blue of the seas. Somewhere down there, beneath that quiet shine, the Great Conveyor Belt is still moving. It does not know we have been watching. It does not know we have been wondering. It simply flows as it has flowed for thousands of years, carrying warmth from the tropics toward the poles and cold water back again, in a loop too slow for any one life to follow. Above that small blue world, the moon hangs in its long, patient orbit. Its pale light touches the open ocean and lays a silver path across the waves. Under that light, the surface looks calm. A few seabirds drift on the swell. A whale somewhere far below moves through layers of water that have been traveling for centuries. The belt slips on unseen beneath all of it. Step further back, and the earth becomes a single bright point among many. The sun is a quiet yellow star on the edge of a slow spiral. The galaxy itself turns, taking 250 million years to make one full circle. We sit on a small ocean planet on one arm of that turning wheel, asking small questions about water and salt and warmth. And the answers, when they come, will come slowly. The way the deep ocean gives up its secrets, one careful measurement at a time, one season at a time, one generation at a time. There is something gentle in not knowing. The belt has been studied for less than 100 years. Sediment cores have only recently begun to whisper their stories. The deep floats and the satellites are young instruments in an old, old sea. Whatever the ocean is doing now, whatever it will do next, most of that story is still ahead of us. We may know more in our lifetime. We may not. The mystery does not mind waiting. For tonight, let the questions rest. Let the cold water keep sinking in the Greenland Sea without your worry. Let the warm current keep brushing the shores of distant lands without your watch. Let the salt and the heat and the slow turning of the planet do what they have always done. You do not need to hold any of it up. The ocean is older than your worries. The galaxy is older than the ocean. And somehow, in all that age and all that scale, there is room for a small, warm room and a soft pillow and the slow rhythm of your breath. Imagine the planet from above one more time. The clouds are moving gently. The seas are dark and bright in turns as the day passes across them. A long, slow current threads through every ocean like a quiet thought. The stars beyond are steady and patient. Nothing is rushing. Nothing needs you to do anything at all. You are held by a world that has been holding things for 4.5 billion years. Mountains, deserts, forests, reefs, the long bones of whales, the soft shells of tiny sea creatures whose bodies became the chalk of cliffs. The belt carries on. The earth turns. The galaxy turns. And somewhere in all of that turning, you are here, small and safe, drifting toward sleep. We will leave the mystery just as we found it, beautiful, open, and unfinished. The conveyor belt of the oceans still moves under the moonlight. Its full story is not yet written. That is a fine thing to fall asleep beside. Thank you for spending this long, quiet night with the deep sea and the open questions it keeps. Rest well. The ocean will keep flowing while you sleep, and the stars will keep their patient watch. And tomorrow, if you like, there will be another mystery waiting in the dark. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.